Question 1 in exercise 7D, we have a particle P hanging freely from a point O. Let's say this is O and this is P. And P has a light inexpensive fluid. We have length L and we have this circular motion. We have gone up this direction. And the string is going to become slack at some point. The angle is less than 90, so it'll be up in this sector. So slightly off scale diagram, but this is L as well. This is L, and it makes an angle. Well, let's leave our angle just as A or theta. Let's leave it as A for now with the vertical, which means that this angle in here will be A. This will be mg. And we resolve the forces for mg. Let's just take my particle P and going towards the center. And I have mg. And the right angle will be here. So we have my angle A. So in here I'm going to have mg cos A. And along here mg sin A. I also have tension in the string towards the center. So forces here we have T plus mg cos A will be equal to my centripetal force m is v squared over r. We're using v squared over r. We're given speed. And r is actually equal to L, so I'll just change it to L. So that's my forces equation. If I look at my conservation of energy and I take position 1 and position 2, position 1, mgh plus a half mv squared will be equal to mg, it's at 0 height wise, and then plus a half m by a v squared is the square root squared, so just 3gl, 3gl. That's in position 1. In position 2 we're going to have mgh again plus a half mv squared for position 2, so this will be equal to mg, and the height, well, we need to work out this x here. So what have we got here? We have radius of L, so it's going to be L cos A. Any other information? Don't think so. This is just going to be L cos A, this side of the triangle. So the height is going to be L plus L cos A. The two of them added together. So L plus L cos A, bear with it, it should work, plus a half mv squared. So what else do we know here? We can get both of these equations in terms of mv squared. So the top one, mv squared is equal to T times L plus L times mg cos A, and that's going to be equal to, if we simplify this guy and get mv squared on its own, I'm going to need to multiply this equation by 2, so that will be equal to this guy on the left, and I'll have to bring this whole guy across, so it's going to be equal to 3 mgl. That's this one by 2. If I multiply this one by 2 and bring it across, it'll just be a minus 2 in front here. Minus 2 mg times L plus L cos A. So that's equating the two mv squareds. We can definitely divide by L maybe first. T plus mg cos A is equal to 3 mg minus 2mg, and if we divide L by L, we're just going to get 1, and L cos A by L, we get cos A. We're trying to show the angle is a third, so we want cos A here. So tension will be equal to 0 just as it departs from the sphere or whatever it's connected with. So let's have a look at tension here. Tension's equal to what's already there, 3mg, and removing the brackets, minus 2mg cos A. And then I'm going to bring this one across, minus mg cos A. So the tension at any point will be mg minus, we have 3 of them, 3mg cos A, and if t is equal to 0, we're going to get mg is equal to 3mg cos A. I can just about see it now working. Dividing by mg, we get 1 is equal to 3 cos A. So cos A when t is 0 will be in fact 1 over 3, which has proven what we were asked to show at the beginning of the question.